We are starting the recording, and I'm giving my tutorial. All right. Like I said, I basically want to talk about how, as a programmer or as a researcher who use LLM as a part of my daily research, how we can use available tools to maximize our efficiency. Because as you know, when we use LLM, we are basically facing a text completion API, or we are just using Hugging Face. But we can do much more on top of that. To begin with, I'm going to do a quick review of what a large language model is, especially what the large language model looks like in 2024. So let's start with what's a language model in its original form. So it's just doing a very simple task of predicting the next word. So you have a sentence that's not complete, a prefix, and you will feed it into some kind of neural network, and it provides a list of possible next words with its possibility, a probability. And you have some algorithm that selects a word from that list, appends that list to your prefix. They get a new prefix and repeat this process, feed them back in the neural network, get another word, so on and so forth. You will, in no time, get a whole paragraph of continuations. That's basically how GPT-1 and GPT-2 works. You have a prefix, feed it into a transformer, a neural network, and get a output probability for the next word. But in 2024, things are not that simple. There are some improvements over GPT-2 for sure. Like the model is much larger. That's why it's called large language model. Major breakthroughs are OpenAI and DeepMind. They spent a lot of money and got the conclusion that the more money you spend on enlarging transformers, the better performance you get. And you can spend the money on either training with more iterations or increase the data set size or add more parameters to the model. And they also spent a lot of money trying to figure out a formula to get the optimal amount of computation, data set size, and number of parameters for the given amount of money you have. And with all this formula, they have very large models that are trained somewhat optimally. And these large models can do a lot of tasks without requiring the users, which is us, to fine-tune the model or train the model with your own data. Like you can just provide a prefix and ask the model to do some imitation completion, and we could get the task done for you. But that's the story of GPT-3. But a shortcoming of that model, mode, is that imitation completion isn't what we commonly need for a smart agent to do things. For example, here, we try to ask the model to explain a moon landing to a 6-year-old child. But instead of explaining moon landing, it just gives similar requests of the same format, which is not what we want. And to make it do the work we want, we have to convert our request to some format like a Q, comma something, and A, comma. It will more probably generate an answer to a question instead of repeat your question in different ways. And to improve the success rate, you can add examples of the same format, which is called in-context learning. But this is not very intuitive. So there's a new thing called instruction tuning and reinforcement learning with human feedback, which is basically teach large language models how to follow instructions instead of just repeat with similar things. So what OpenAI did is they hired a lot of people to create instructions and their responses. And as step 2, they hired people to they used GPT-3 to generate responses for all the instructions they created, and asked human to rank different responses for the same instruction, so they can have a model that have a preference on which response is better. And with this model, they can just build on top of each other to do some reinforcement learning, make the model better without any human intervention. That leads to what we have for ChatGPT and GPT-4, which is you can just give the instruction, and if you understand your intention, give the correct answer. And finally, at the output side, models in 2024, they are mostly trained with a tool calling, which is people will synthesize some data to make the LLMs aware that there are many tools they can use to, there are many external tools they can use to help complete their tasks. Like they can search Google or use some calculator or use some external machine learning models. They just synthesize a lot of data. And the outcome is now you can just provide a list of functions that you want the LLM to use. For each function, you provide its signature and its maybe a doc string, what each parameter does. You give it to the LLM, and at an appropriate time, LLM will output the most suitable function call without the correct parameters. So these are what makes large language models in 2024 different from simple next word prediction in the age of GPT-2. And all these 3 properties, they will be very useful for all the different things we want to do with large language model. So far, is everything clear? Okay. And from a programmer's perspective, we want to do a lot more than just next word prediction. We are building things. We are using large language models to generate data, to do evaluations, a lot of things in research I'm talking about. And if you're building applications, there's certainly a lot more things you want to do. So at this section, I'm going to go through what a programmer or a researcher using LLM is going to face if you are just using the API. First, at the input part, we have to do a lot of operations to the prompt. I'm calling it gymnastics because there are many not very systematic, principled ways to tune the prompt or tune the input to make perform better on the same task. But the most basic thing is we need to describe our task. This is the basic thing. But it's often not sufficient. For example, if you are doing math and you directly ask for the answer is usually wrong. Intuition behind this is a complex math task is usually not in the training set, and it's very hard to get it correct. But if you somehow guide the LLM on how this question can be answered, like the middle steps of getting this done. For example, you provide step-by-step instructions for one of the examples and ask the LLM to follow the same step to decompose the complex task into multiple smaller steps and answer each smaller steps sequentially. It's more likely to get the answer correct, which makes sense because the smaller, easier steps are more likely to appear in the training set and more likely to be learned by the LLM. It has the ability to answer complex questions. It's just us as the programmers have to guide the LLM on how to do it. Besides providing steps, we have to provide examples and maybe find relevant documents from your own databases or your own corporate knowledge bases. It's a very hot thing in the industry called retrieval augmented generation. But basically, you have to provide relevant documents in your input. These are just some examples of what we have to do with the input. And when we do feed the input to the LLM, we also want to somewhat control the next word prediction. For example, when we use ChatGPT, we can see a phenomenon that the output is usually organized in different points. Like if you ask a question, it will give multiple points in a bullet point style, and often those points, they are not dependent on each other. So we can leverage this property to make the generation in parallel to speed things up. At the output level, we are usually not satisfied with just the whole raw text, the lengthy text answer provides. Instead, we have to write code to parse the output to find exactly what we want. For example, we're asking for a date. We might need to use regular expressions or something to extract the date from the answer. And at the output side, we can also do some guidance to improve the quality. For example, we know we are going to generate a list, but the LLM generation might derail and generate something else. But if after each point we manually add a bullet point or add a number, we can sort of force the LLM to stick to the list format and get better results. And finally, following the same sense, we can add more constraints to enforce the generation to follow some formal grammar. For example, ChatGPT now has a JSON mode, which forces the output to be in JSON grammar. Similarly, you can supply a regular expression or context-free grammar and force the generation. But the premise of all this is the language model itself is capable of doing the generations. You just need to add some limits to make it better. That's the output side. And putting those things all together, sometimes we do need to make multiple LLM calls for the same task at hand. For example, as a first step, we ask it to generate the step-by-step reasoning process. At the next step, we extract the reasoning from the previous output, append them to a new input, and directly ask the LLM to answer the question based on the reasoning steps. Well, this is sometimes called flow engineering in recent months. One of the very successful framework is called React. So it's using this multi-step LLM calls to make the LLM interact with an environment and do actions. And that each step consists of think about what you should do and choose an action from a list of actions. And then you'll be given the observation of the outcome of your action. And you repeat this process to think more about what you did wrong with the previous step. Like if you chose the wrong action, if something else, your thought, your rationale wasn't correct enough. And in the next round, you can make corrections or do other actions. But basically, this is an application of how we can combine all the three parts together, make massage to the input model, the output, and putting them all together, make a loop, and build some very sophisticated applications just by using this for loop in the style of React. In the style of you think, act, and get the observation and repeat. And this is Devin. It's most hyped AI thing in March 2024. They got a lot of investments. Basically, they are doing is to build a system based on LLM that can autonomously do software engineering. What the user has to provide is just a very high level instruction. For example, the user asks Devin to compare the performance of Llama 2 from 3 different providers. Once you have this very general idea, behind the scene, Devin uses the React framework to iteratively think and reflect on the current situation, choose some action, use tools by calling some API, and it uses different tools like a planner, which lists all the to-dos, and a shell that executes commands, a code editor that writes code and makes changes, a browser that searches documents for the API calls, and magically it builds a website that visualizes Llama's performance from the 3 different providers, just by combining all the different tools, all the different functions and abstractions we talk about in the React framework. Well, actually, Devin is we only have some video previews available. We don't really know what's happening. We don't really even know if it's fake. Some people say it's fake, but there are some research groups are trying to replicate the thing, and they used the React framework, and it worked at least. So I assume then it's the same. It's a similar story. Okay, that's all the function. That's all the things as programmers we have to add on top of the basic large language model calls to build applications. So in the next section, I'm going to go through available tools and frameworks libraries in the open source community or in the academia that tries to make that tries to make all the operations easier. An interesting blog post I read earlier from 2 Sigma. It tries to make an analogy between computer network and large language model. In computer network, there's an abstraction model called the OSI model. Basically says at each layer you only have to care about what interfaces are provided in the previous layer. I don't have to care about the implementation of the lower level. Like if you're writing an application, you don't have to consider how information flows in your cables. And these people from 2 Sigma, they're saying we can have a similar abstraction model for all the libraries for LLM, also in 7 layers, because 7 is a magical number. It's a good blog post that covers some more tools than what I have in this presentation. But here I'm just copying their abstraction model, trying to group the things I found interesting from bottom to the top level. From the bottom level is just you're directly interacting with some neural networks to do the next word prediction thing. And for us, we are using a ChatGPT using the API from OpenAI, or we are using the transformer library from Hugging Face to run some local models like Llama 3. But the Shraj is making a new batch API for Llama 3 70B instruct model. In no time, we'll be able to share the model very efficiently. But back to our story. At a very basic level, we are doing very raw string manipulations. The input is just a string. The prefix we want the model to complete. And for Hugging Face or OpenAI, we just feed the prefix into the API it provides. And behind the scene, not behind the scene, it generates the next word probability for the current position. But normally there's a easier way to do this. Like there's a generate method in Hugging Face that help you choose the best next word in the current position, make a new prefix, do this thing repeatedly to generate a whole sentence. But it's basically doing the same steps, in a loop. It's very basic, and at the end you get a raw string from the model. And one thing to note is after ChatGPT, we are not directly sending a prefix to the model for completion. Instead, we are sending some messages in the role of a system message, a user, then the model gives some response as an assistant to what the user has said. But this time, behind the scene is just as simple as a string completion. So there's a template that applies to the messages that converts the messages into a string. There are some special symbols that indicates which part is spoken by which role. And the model just does completion after this formatted string. In OpenAI's model, in OpenAI's API, they will do some post-processing on the generation and send the whole thing as what the assistant has said to you. But if we are just using Llama locally, we can actually have more control. Like we can make forced constraints on what the prefix of the assistant response is. Like we can force the system to say, here's the steps, here's how to solve the problem step by step, comma. This way we can have more control and get better results. But the message here is, the chat interface is just another wrapper above raw string completion. And when we are dealing with raw strings, I personally have some favorite tools for writing and managing the prompts. First thing is YAML. It's a format to write configurations or data format. It's kind of like JSON. It's a representation of data, but it's designed with human readability in mind. So instead of having all the brackets, codes that's better for machine to parse, YAML is very clear. You can write it in many flavors you like. If I remember correctly, JSON is a subset of YAML. So if you prefer JSON, you can use JSON. But the good thing is, normally you can write much more readable things to put your prompts in. For example, you can write comments, which is not supported by JSON, or if you are just using it has built-in comment support. And if your prompt is very long, you can arbitrarily add a new lines to your prompt. And the YAML library, when it parses the thing, it will automatically remove all the line breaks, remove all the indentations. So it looks clear when you use it, and in the program, all the auxiliary things are gone. And if you write a multi-line prompt, it stays multi-line in the YAML file, but in JSON you have to write /n something. It's very hard to manage. But here you can just use different styles of multi-line strings to keep them organized. Another thing I want to talk about is Jinja. It's also for writing prompts, but it's a template language, which means it does string interpolation. When you use Jinja in Python, you can provide some variables or dictionary, and Jinja will replace these placeholders with the variable you passed in. And the much better thing is you can even write comments within your prompts. For example, you ask ChatGPT to use certain format options, give it certain hints, but you want to tune which instruction you give works best. You can just comment things you don't want out. And it has built-in loop and condition support, so you can very easily write things for in-context learning without considering how to format each example. But these are just for the case you want to deal with the Hugging Face or OpenAI APIs directly. These things can make your raw string manipulations easier, but they are not better, but higher level tools that can somewhat free you from dealing with raw string concatenations and interpolations. In the previous section, I talked about all the features I, as a programmer, will have to implement if I'm building something on top of LLM. And for each subset of all these things, there are multiple libraries on GitHub or some commercial tools to help you do some of this. And there are so many flavors you can basically choose whatever you like. I'm just giving a few examples. LMQL here is a domain-specific language for controlling LLM, which means it's not Python. It's not some existing language model. It's not some existing programming language. It has its own grammar, sort of like SQL and Python combined. But to give the instruction to LLM, you just write a top-level string, and it has SQL style controls for when the generation stops. And after the LLM generates something, you can append things to the generation. This way, you are providing guidance on how the generation goes. For example, you previously gave you ask the LLM to generate an answer. The answer can be a string, but the question itself is actually it's asking for some arbitrary thing. But if you want to extract a more specific span of the answer, you can append the answer is to the prefix and guides the LLM to extract the exact answer. You can add constraints to the answer. Here is asking for an integer, and LMQL is modifying the list of probabilities for the next word to make sure the next word chosen matches the constraints you have. And here, the answer as a type int is stored in a variable called num. But going forward, things are more coupled with LLM. Like this is LMQL, it does all the things we want. After you write the thing in its DSL, it is converted to a Python function and just call it and get the number in the previous step. But maybe some people might, like I said, all these things, there are so many functions we want to do, and there are so many libraries that implements these functions. And you can choose anyone that suits your flavor. For example, guidance. Guidance it does the same thing as LMQL, but it's not a new language. It's just Python with some function with some new functions, not new functions, with some functions in some libraries. So same thing, sending the request in guidance flavor is doing concatenation to the string. Similarly, it has the same function. You can control when the generation should end. Like it must end at a period. And you can constrain what the output is like. Here, I'm 100% certain what they do is once they get the output, once they get the output probabilities, they remove the words that doesn't match the constraint from the list of next words. This way, they are forcing the generation to follow the grammar. So for LMQL, I think they did something to the activation through weights to the model to make it more likely to have higher probabilities for grammarly correct next words. But here it's just brute force. They filtered all the words that doesn't fit the grammar And the grammar can be, you can choose from some options, or it can be a regular expression, can be a CFG. And the answer can be stored, automatically extracted, stored in a variable. Here's the answer. And you can access the answer from the previous call without having to stop the generation yourself, locate the answer, extract the answer, and resume the generation. Here you just write them as a single flow. And you can do branching based on what was previously generated. And again, you can manually add some output as a prefix to LLM's answer to guide the generation towards the direction you want. And believe me, writing them manually is very time consuming, especially if you want to have high efficiency. Okay, that's guidance. It's the same thing as LMQ. I can do all the loops, all the controls you want. And there's an extension called sglong, which adds some parallel primitives besides the gen and select primitives. So now there's a fork in the scenario that I could talk about where the LLM has multiple perpendicular or independent points to expand on. It can be done in parallel to be more efficient. And sglong provides some compilation thing that analyzes the data flow of your program, finds what can be run in parallel automatically, and does them without your intervention. But all this requires you to write some program and run on some local engine, which means all this fine-grained control cannot be done on OpenAI API or any API available on the internet. You have to locally run Llama to use all this control. And Microsoft, they tries to, I guess they are making a step towards solving the problem I mentioned. They are trying to provide some interface for all the control you can do. And they have runtime. They hope maybe LLM providers, they can use their runtime and ask users, we can write the control code in any flavor we want, compile them to what's compatible with the runtime, upload to their cloud. Maybe in the future, if this gets adapted, we will be able to send the fine-grained control code to OpenAI to actually make more constraints in the generation process. And this thing, Devin, is what you talk about. Simplify is fine, like without using any engine, you can just write, just describe what you want in any kind of language and feed them directly to the LLM. And if the LLM is very powerful, like GPT-4, it understands what you want and outputs in the way you asked. So it's possible to do all the control without engine. You just write what you want, send them to GPT-4. The message here is with a much powerful LLM, we don't even need an engine. We don't even need to learn some programming language. It will follow instructions better and better. So the need for external engines might be lower. But that's it for these things. For these low-level operations that we can do manually if we want to make LLM run better. But there are all sorts of tools in all different flavors to help us do this. And moving to the next level, it's about using LLM at the implementation for at the rough implementation, at the crude implementation for any arbitrary any arbitrary function in computer programming. And I'm making a proposition. I'm not me. Many people are making the proposition that LLM can substitute for some hard to implement function. It's not just for LLM. Like when we have neural networks, machine learning, what we are doing is we have a task that's very hard to write an exact program to solve. So we gather a lot of data. We train a model to try to approximate that function. But here with LLM, it gets even easier because of all the instruction following, all the zero-shot learning capabilities. We don't even have to gather the training data. Let's say we are given a list of animals to try to find a word to describe them. If you are asked to write a program to do this, it's probably very hard. Maybe with the help of some knowledge graph it's possible, but it's hard. Another example is maybe you just want to generate some fake data. You don't care how it looks. And to implement such a function, you might need a database of names, a database of addresses, and do the sampling compositions. It can be hard. An alternative is to gather data, train neural networks. But with LLM, we don't really have to gather data or train things. It directly provides us with an abstraction. That is, we know sort of what we want. We write a function signature for what we want. And then the LLM provides what we hope the function will do. So that's sometimes called an oracle, if my understanding is correct. And again, there are libraries, tools, work that tries to do this abstraction. One of them, DSPy, is built by Stanford, I think. They are making the analogy that LLM approximates functions in the sense of computer program functions. And neural networks, they are approximating functions in math, where the domain is real words, the real numbers, and maps real numbers to real numbers. In LLM, you map some computer programming data types to some data types. We think since this thing has some analogy, we can build tools that are similar to what we use, what tools we have for neural networks to approximate math functions. Which is they are basically copying PyTorch API for LLM function approximations. And the oracle I talk about, in this example, they're doing question answering, and they only want an oracle that it takes in a question, outputs an answer. And in the DSPy framework they have, you can just write a shorthand function signature, input is question, output is answer. Here, because the function, because the input name and output name has some meaning, language model can sort of infer what you want. And even though you just provided us 3 simple words, the LLM can already serve as a function where you provide any question, it will give you an answer. And when DSPy people making the analogy to PyTorch, they are saying DSPy.predict, this thing is like an end-of-module. End-of-module in PyTorch, it's a representation for a function. And speaking of function, there's a composite function. And in PyTorch, you are wrapping end-of-module inside another end-of-module. And in DSPy, you are also wrapping a DSPy.module inside DSPy.module, where you are calling the function you previously defined. Like here, you are actually this chain of thought thing. It can convert any function with the capability of doing chain of thought reasoning. So what it does is it takes the input, but prepends, let's think step by step to get some rationales, and finally use the rationales to get the answer. But it's done in the style of a composite function. And in DSPy, all the prompt engineering is in the style of composite function. Or in Python, you're writing a class that inherits from DSPy.module, and that class is doing composition by having other DSPy.modules as its member variables, if I remember what the OOP thing is correctly. But then the benefit here is you don't have to copy and paste all the prompts for different prompt engineering things. Like in chain of thought, you have to copy paste, let's think step by step to any task you have. But here, you just write it as a composite function, and it does the copy paste for you. Same thing with retrieval augmented generation. The final analogy they have is in neural network, we can have some training data to tune the parameters of your function to make it work better. And they are making the analogy here for large language model that if you have a training set, you can find a subset of the training set for your in-context learning prompt. You can provide some examples to the LLM to make it work better. And in DSPy, they provide they call it a compiler, but it's what it does is it tries to do some optimization to find the best subset of your training set that when it's appended to the prompt as examples, it makes the LLM work best. That's DSPy. Supposedly, it makes prompt engineering very lazy. You just want a function. It's hard to write it yourself. You don't want to train some PyTorch models for this. There are tools where you can just write your function, define all the types, write a docstring, describe what it does, and these things instruct fructose, they can build these functions for you, where the function implementation involves calling large language models. And we directly use the function calling and tool use capability that are trained, that the 2024 large language models already have, to make sure all the types of the input and output are correct. Or maybe some work they try to use the grammar constraints to make sure the types are correct. And all these things, if you already have a thing that roughly works, adding those constraints, like adding types, will increase your rate of success. But if you're not sure it will work, my suggestion is don't blindly trust anything. So that's about using LLM for the Oracle. And there are some interesting applications for this property, that LLM can be oracles. It can execute, it can be any. It can be the implementation of any arbitrary function in programming language. For example, in December, there's a paper from Google. They are combining this capability to do some tasks that are hard to do if you write pure Python, and it's also hard to do if you directly use LLM. Like in this example, it's asking to count how many countries they have been to, based on a list of locations, but the locations they are not at the same granularity. Maybe there's a city, there's a place, there's a country. And their approach is a mixed approach. They ask the LLM to write a Python program for this, so you can convert things to a list. You can have for loops. You can have sets for deduplications. You can have the len function to correctly count things, which is something can't do reliably, counting things. But for the tricky part, like how to map a location name to the country, it asks the LLM to write a function call to a fictional function get country, and it doesn't require the LLM to actually write the code to implement the get country function. Instead, they are running the entire code in a Python interpreter. The first line can be run in Python, second line can be run in Python. At the third line, interpreter throws an error saying there's no function called get country. At this point, they delegate the execution of this function to the LLM. It provides the LLM the current states of all the local variables and the function name. The LLM returns with the return value for the fictional function. And then it continues back to normal Python execution. So that's I think that's a good example or good application of using LLM as the oracle. Here, the program itself is written by LLM, but I guess there can be some neat scenarios in our daily use where we want some sort of function, but we really don't want to, but we don't know how to implement it. And we can delegate it to LLM. There's a follow-up to this, which does it in a more meta level. They are compiling many tasks of the similar nature to Python code and use LLM to directly execute the Python code. If I understand correctly, they got rid of the real Python interpreter. Instead, they directly use LLM as a Python interpreter. And it also worked at least on those tasks that involve both some rigorous logical thinking and some places where approximations can be helpful. You don't have to write the code. You don't have to write the implementation for the function. You just need the signature. That's my message. The final part is I'll be very quick, but it's most hyped thing in 2024 using LLM as agent. From the user's perspective, you just give a high-level thing, and the LLM agent it autonomously does all the things for you. In the more technical perspective, you are combining LLM to do both all of perception and planning and action. The Devin thing I showed is one example of LLM agent. I have another example that I find interesting. It's for doing memory management for LLM. What the problem is trying to solve is LLM has a fixed length context window. For example, Llama 3 can only process 8,000 tokens. So it's kind of similar to computer memory, where you have a limited number of memory, but the Turing machine assumption assumes you have an infinite length tape. So what operating system does is it provides an abstraction. It gives the process an illusion of infinite length continuous memory space. But behind the scenes, the OS does some virtual memory thing that makes that stores the information at different places other than the main memory. This MemGPT work, they are trying to replicate the memory management system for LLM. So everything is done purely using the function calling capability of GPT-4. So they defined a series of functions for all the memory swapping operations. And they ask GPT-4 to conduct a conversation with the user. And they have an external thing that monitors the context length. If the context is almost full for the window, it sends a system alert to GPT-4, which is an analogy to interrupt in operating system. And once GPT-4 sees the system alert in its prompt, it automatically chooses the correct function to swap some things in its memory to some external storage. So here is it automatically selects what it sees as important to be stored in some external persistent memory, and the engine MemGPT has will store these things in some files and remove them from the context to free up some space. And conversely, when the conversation mentions some new concepts that's not in the memory, currently, GPT-4 will automatically select the correct function from the function list it has to search the external storage, find related things, read them back into the context, to the context window. It's sort of similar to read-ahead operation and swapping in operating system. And externally, in the engine they implemented, they have some FIFO thing that also manages the memory. But most of the operations are purely done using the function calling mechanism that GPT-4 already has. So with that, it builds such an agent that manages its own memory to have a illusion of infinite memory, infinite context window. This is just another example of agent, but it's the most type thing in both research and maybe investment. I'm seeing a lot of things, a lot of news about LLM agents. Okay, that concludes my tutorial. First, we went over what good properties or good capabilities large language models in 2024 has, such as they can follow instructions, they don't require training, and they can call functions. And by building on top of these things, there are so many different tools and so many different levels to choose which how you want to build your application. At the base level, which I use the most, there are already things of different flavors to save you from writing the code to do the parsing, writing the code to create format the templates for the prompts, to write the code to call LLM in multiple runs. If it's you are lazier, there are tools to directly just write a function signature and let LLM do the rest. Finally, the latest hype is we don't program. We just provide a high-level thing that the agents figure them out